Okay, so what we have talked about is about the fixed biased, where I have drawn this circuit again here. So we have the circuit here, and this is called the fixed bias circuit. So one of the features about this circuit is that it is highly sensitive to variations in the battery voltage VCC. So we want to look at other biasing schemes as well. So there are many other biasing schemes. Another very popular biasing scheme is called the potential divider biasing. Okay, so potential divider biasing is another biasing scheme. In this particular case, what we do, similar to what we have earlier. So what we have here is a similar circuit, except that the biasing is obtained using a a voltage divider, a potential divider circuit, as shown here. So how do you find the quiescent point, the Q point? That is basically VCE, Q, and ICQ under this condition. Okay, so this is what we are going to look at now, and how are we going to achieve the quiescent condition here. Now, if you can see, it is not as easy as the previous case, because now unless R1 and R2, these two resistors are very small, so that the current through R1 and R2 is much bigger than the current IB, you cannot actually find the voltage at this point, the base, directly. If in fact R1 and R2 are very small, so that the current going to R1 and R2 is much bigger than the current IB, then of course we can ignore IB and assume that the voltage here is just the potential voltage ratio as a potential divider. So it will be R2 over R2 plus R1 times VCC. But unfortunately, not in all cases it is like that, especially because if you choose R1 and R2 to be very small, there will be a larger current going through this. Typically IB is in the range of microamperes for small signal amplifications. So it's certainly less than several milliamperes. So therefore, in order for that, let's say 1 milliampere current to be very small, the current through R1 and R2 has to be much bigger. Say for example, the current should be 10 or 100 milliamperes, which requires R1 plus R2 to be in the range of like 100 ohms or so. So 100 ohms or maybe 1k or something like that, in that range, so that if VCC is 10 volts divided by 1k would be 10 milliamperes. So at least that, so this should be less than that. But the problem in that case is this is just there to maintain the voltage at the base, and that current passes through R1 and R2, and I squared R losses will be there, which is not contributing to our uh, signal. So therefore we do not want this R1 and R2 to be really small most of the time, so that to reduce the power dissipation, the fixed power dissipation across these two. So typically we want these to be rather high, so that the quiescent current or the current through R1 and R2 is small. So in such situations, IB may be in the same range as the currents through these R1 and R2. So this may be I1 and this may be I2. They may not be the same in general. So how do you tackle that? So the way to do this is by using the Thevenin's. How to find IB we use Thevenin's equivalent circuit. Thevenin equivalent circuit of the bias circuit. Okay, so what is the bias circuit? So if I draw just the bias circuit, it would be just R1 and R2 connected to the, so let me draw it here. So you have the VCC, R1, R2 and the ground plus VCC, and you have the base here. So what I want is the Thevenin's equivalent circuit of this circuit. So that would be, I have Thevenin's voltage source and a Thevenin's resistance RTH and VTH. I want to find these two things so that I can connect this directly there, like this, RTH and VTH. Okay, so what are the values of RTH and VTH? So let's find that. It is not hard to find it. Obviously, if you take this circuit here, the bias circuit, it's easy to know that the voltage at B, so open circuit voltage is the same as VTH. So if you don't connect anything here, output will be VTH. So if you don't connect anything here, output will be the VTH. So VTH is easy to find. That should be R2 divided by R1 plus R2 times VCC. So it's the potential divider, right? That's easy. And what's RTH? That's also not too hard to find. There are many ways to find it. One way to find is basically short circuit the terminals, so that if I connect the terminal here to ground, right, as like this, like that, so I should get the same current, should be the same. So therefore using that I can find, I know the VTH, I should be equal to VTH divided by RTH, which is also equal to, I can apply the Kirchhoff's voltage law if I want to this or this loop, right? So either way I can find my RTH as, so if I apply the, so you know, if I short circuit this, there will be no current passing through R2. The whole current will pass through R1 and go like that. So this is basically I, and this will be I2 is equal to 0. Okay, so the same current will flow through R1. So what is my I1 then? That should be equal to VCC divided by R1. So from that I can find VTH, which is R2 over R1 plus R2 times VCC times R1 over VCC is equal to RTH. So this is one way of doing it. There are other ways of doing it also. So my RTH is equal to R1 R2 over R1 plus R2, which is actually nothing but R1 parallel R2. Okay, so the parallel equivalent circuit of R1 and R2. This is easy to find. There are many ways to do it, so we can find it. Okay, so we now know how to find the Thevenin's equivalent circuit of the bias circuit. Now once you have the Thevenin's equivalent circuit, it is not that hard to find the quantities in our circuit. So how do we do it? So first we'll find the IB, it's the current through the base IB. To find IB, I can apply the Kirchhoff's voltage law in the base emitter circuit like that. Okay, so what are the voltages we have? We have the VTH like that, VTH. I have RTH, IB is flowing in this direction, so this is I base times RTH, and then you also have VBE like that. Okay, so those are the three things that you have. So if I apply Kirchhoff's voltage law to base emitter loop, I have VTH is equal to VBE plus IB RTH. So IB is equal to VTH minus VBE divided by RTH. We know both RTH and VTH, and VBE, this is equal to 0.7. Okay, so therefore I can say this is equal to R2 or R1 plus R2 times VCC, that is VTA, minus 0.7 divided by R1 R2 over R1 plus R2. So you can simplify if needed, but basically you can find an expression in terms of known quantities for base current. In fact, this is at these are the DC conditions, so therefore this is the quiescent base current or IBQ. Okay, so once we know the quiescent base current, we can find the quiescent collector current IC, because we know that this is in active linear region. That is why we bias it to make sure that it is in the preferred region. We want it to be in the active linear region, so IC is equal to beta times IB. So ICQ therefore is equal to beta times IBQ, which is equal to the above expression times beta, right? So ICQ is also known. So it's basically the beta times the previous expression, beta times IBQ. So now the next thing that we need to find is the quiescent VCE. To find that, we need to apply the apply VCC, the Kirchhoff's voltage law, to the output loop, that is this loop over here. Let me undo what I did. Okay, so it should be to this loop like that. Okay, so what voltages do we have here? We have VCE, this voltage here, and only this IC times RC, and that should be equal to plus VCC. Okay, so therefore let me write VCC is equal to VCE plus IC RC. Therefore VCE should be equal to VCC minus ICRC. We know what IC is, that should be equal to ICQ, so therefore VCEQ is equal to VCC minus ICQRC. Okay, so we know this value also, so you can write it as VCEQ is equal to VCC minus beta times RC times ICQ, which is the expression here, this expression here, which I can also write as beta is also here, expression in this expression. I can also write this as VTH minus VBE over RTH from the previous expression. So this is the IB, beta times IB times RC, right? So we can write it like that. So this is the quiescent condition of this circuit. So we can find the quiescent condition like that. So we know all the expressions, all the terms in this expression as well. We know the VCC, we know beta, we know RC, we know BBE, which is 0.7, VTH and RTH we already found. So we have VCEQ as well as ICQ. So this is the Q point of this particular circuit. Now notice that when we wrote the equation here for the output loop or VCE loop, we could rearrange this particular expression, this one, into this form. IC is equal to VCC minus VCE divided by RC. Okay, so it's the same expression. I have removed the quiescent condition. This is the general expression. It's basically this expression here I'm taking. So I have this. So what this ends up happening is, what you have is minus 1 over RC times VCE plus VCC over RC. Now if you carefully look at this, what this is just an expression between IC and VCE, and it has few other terms which are constants actually. So RC is a constant, VCC is a constant, and RC here again, this is also RC, that is also a constant. So therefore what you have is something like Y is equal to MX plus C, where M is minus 1 over RC, and the intercept, M is the slope of the line, straight line, C, the intercept, is equal to VCC over RC. And what is this curve about? X is VCE, Y is IC. So this is basically IC versus VCE. Okay, now where did we see IC versus VCE before? If you remember, when we looked at the transistor characteristics, we said the transistor has to behave in a particular way. So the relationship between IC and VCE has to obey a certain rule depending on the properties of the transistor. Okay, so let me draw that again. So this is basically the transistor characteristics, IC versus VCE, and you saw there were some parallel lines corresponding to different values of IB, right? These different IB values, they had different collector currents. It could be 1 milliamperes, 2 milliamperes, 3, 4 milliampere, as such. It could be different values, but just an example. So this is basically depends on the transistor. It solely depends on the transistor properties, nothing else. So it looks like this. But at the same time, now this equation that we have derived right now, this equation right here, also has an expression between relationship between VCE and IC, because this is the Kirchhoff's voltage law applied to the output circuit. The current IC and VCE should also obey this particular rule, and you can see that the straight line has a positive intercept and a negative slope. So what this looks like is something like this, something like that, where this one is the VCC. This is basically VCC divided by RC. So this is RC, okay, and so that the slope is minus RC. So this is the slope. So slope is basically minus. You can verify that this. So what that means is, because this transistor is in the circuit, external circuit that we have here, this circuit here, this one, because of that it has to obey the Kirchhoff's voltage law. At the same time, it also has to obey, so if the Kirchhoff voltage law is obeyed, then the operating point, the Q point, should be on this green line. This green line, it should be on the green line. But at the same time, since this is also on the this is the transistor that we are talking about, this transistor obeys these characteristics depending on the value of the quiescent current. Let's say this IBQ happens to be 30 microamperes, in which case this has to obey this particular line. Okay, so because of that, at this particular instance, it operates both on characteristic curve as well as the straight line that we have drawn here, which only depends on, it doesn't depend on the transistor, it depends on the external circuit. See, it doesn't have any information about the transistor. All it has is the external values, RC and VCC. Those are the only things. Okay, so it's the external. So we call this the load is RC typically for this. So it also, so therefore we call this the load line. So particularly this is because we are only looking at the DC values, we call this the DC load line. So the DC load line, so operating point should also be on DC load line in addition to the characteristic curve. So there is only one such point where both these curves intersect, that should be this. So therefore this should be my Q point. So what this means is, even without actually going through any of these calculations, I could have found this Q point graphically if I knew my transistor characteristics and my RC and VCC. Then I know the load line. If I know RC and VCC, I know the load line. If I know in addition the type of transistor I use, then I know the transistor characteristics. Then I can obtain the Q point if I know my input current IB, which is basically depend on the biasing. So if I know the bias current, then I basically know the operating point directly. So let me give you some notes here. Let me write it down.